Hello everyone. We will continue our discussion about network flow and Ford-Falkerson algorithm to find the maximum flow. Remember the algorithm was that we actually used the idea of creating the residual graph, and basically the algorithm just iterates over the graph and try to find some paths from the starting point, some paths from the start node to the target node in the residual graph, and continues until there is no more path. It's not possible to find a path from the source to the target. So in this video, I'm going to talk about the time complexity of the algorithm and some other actually small details, how we can find the path, and different actually issues that we might actually encounter. So the first question here is that, okay, in the algorithm, I just said that, okay, you keep finding an augmenting path in the residual graph. How we can find a path? Finding a path in the graph, I think that's not difficult. You already know that if you have a graph starting from a node, if you have a starting point, you can search for a path. There is no restriction on which path you are going to take. You can simply use a breadth first search or depth first search to try to find a path. Better to use the breadth first search. You can use breadth first search to find a path from the starting point to until you actually reach to the target point. From the source to the target. Okay, so the cost of finding each path is going to be O of the number of edges, or if you choose to show it as m and n the number of vertices and m the number of edges, that's going to be O of m. And finding actually the capacity here, of course, is going to be at most again equal to it's going to be equal to the length of the path. So this part is going to be O of n, the number of vertices along that path. All right. This part is going to be actually just O of n as well. So the main actually tricky part is that you need to find the path. This is going to be O of m. It's more costly. And the other question is that how many times this while loop will iterate? How many augmenting path it is possible to find in a graph, in a residual graph, in fact. So that is the question. But before I, in fact, go further in analyzing the time complexity, let me show you an example that helps us to do the time complexity analysis. Look at this graph. As I told you, we didn't actually put any constraint on which path we are going to take in the Ford-Falkerson algorithm. So now assume that in this graph, although it is possible to find, for example, this path or this path, this path and this path. So in that case, if you are lucky and you find these two paths first, then you find the, the amount flow of 200, and that's going to be exactly the maximum flow, and that is the best, and just in 2 iteration of the while loop, right? But because of this edge here, and we don't have any constraint on which path you are going to take, it is also possible that instead of taking these paths, these 2 paths, in fact you can simply go with this path. And because of the bottleneck that we have here, so the path is going to have the flow of 1. Although it doesn't mean that you cannot find that correct answer. The fact is that after you actually choose this path and use the flow of 1 here, what would happen is that in the residual graph, you would actually change the edge of the direction of this edge, and the direction of the edge will be actually it's just actually just it doesn't the figure doesn't show it, but in the residual graph, the direction will be actually switched, and then you can actually still find another path, and the number of iterations in that case is going to be 200 different iterations, and that's a lot. It actually just shows you that the some issue with this algorithm, that because we are not forcing to say which path you are taking, and it's not really easy to say that which path really is going to actually be the best path. It is possible that in the Ford-Falkerson algorithm, the number of iterations really goes up until let me actually just give you an exact maximum value. If assume that the maximum number of actually number of iteration is going to be called f star. So this f star, we don't know how many exactly, but it can be as worse as the number of vertices multiplied by the maximum flow that you have over the edges. And this example exactly shows you what would actually happen in the worst case. Something like this, that okay, so far we have already actually sent one flow over this graph, one flow here and one here and then one here, and then in the residual graph, what would happen? You are going to actually have an edge here with flow of 1. Then you started sending another flow, and it is possible that you use this edge on the residual edge and go with this, and again you add another flow here. So in that case the flow is going to actually change to 2, and again in the residual graph actually this is going to 0, this is going to be 1. Okay, so it's just like you increase the flow to 2. Still there is a path. Still you can find this path from here and go to this edge and this edge. So along this path you are going to use pass another flow 1, and the reason is that this edge here is just like a bottleneck for you. And it took me how many iterations? 4 iterations so far just to pass this 4 flow that I already have here. So basically each time I'm just increasing the flow by 1. Although it was possible to send the 100 flow over this path and 100 flow over this path. It was possible, but it is also possible that we actually go with the other path. It's just because we didn't actually put any constraint over the path that we choose. That's why in 1970s, you can see that everything here is very recent. Ford-Falkerson proposed this algorithm, I think a year or 2 before. And then in 1970s, Edmonds and CARP actually just tried to modify the Ford-Falkerson algorithms and try to find some approaches to make sure that the number of times that you find the augmenting path is going to be kind of polynomial. So they proposed 2 different actually approaches to find the augmenting path. Instead of actually keep it as an arbitrary path that you choose, they suggested that you can just go with the shortest augmenting path. What is the shortest augmenting path? To find the shortest augmenting path, they are not going to use the capacity of the edges as the weight. They don't consider the capacities at all. They just consider the weight of 1 over all the edges, and easily you can actually use a breadth first search to find the shortest path from the source to the target on the augmenting on the residual graph. Okay, so The shortest path is just based on the number of edges, so the path with the minimum number of edges. So the cost of finding the shortest path is going to be BFS, that's exactly O of m plus n, and we can actually prove that the time complexity of this algorithm, I mean the new modified version of the Ford-Falkerson, that here we call it Edmonds and COMP algorithm, the time complexity is going to be m power 2n. So in fact, they tried to prove that the number of time that in our algorithm the while loop will iterate is going to be O of m to n. The proof is a little bit actually, complicated to go over it completely, but it is in your textbook, and I thought that that's going to be much more clear that if you read it in the CLRS textbook. But if I wanted to actually give you some idea, the fact is they are saying that every time that you are actually finding a path in your residual graph, at least you are changing, you're saturating one of the edges in your graph, right? Because every time you find a path and you actually find a bottleneck on that path and you add that flow to the value of your flow, and so it's just like you're saturating the value on that edge. In this way, it's actually just make sure that at most you are going to actually saturate E number of edges, right? So, and the number of times that you are actually just, and you need to multiply that to the number of vertices, and that's going to be the maximum number of times that you find a path in the Ford-Falkerson algorithm. So, in fact, using this idea if I apply it over the previous example, it exactly just shows you that, for example, the shortest path is going to be about with 2 edge here, and another shortest path about with 2 edge here, and just in 2 iteration it finds the Edmonds and COMP algorithm will find the correct answer. The other approach that they considered was choosing an augmenting path, which is the fattest path. What does that actually fattest means? They define it based on the value of the capacity of the edges. So in your residual graph, you try to find a path that has the maximum bottleneck value. So that means that that path is going to have actually, it's kind of why we call it actually the fattest path. So it's just like that bottleneck is bigger. And if we actually apply this algorithm over, for example, this example that we have, you can also here see that how it actually works here. In this example, I just try to actually, in fact, show you what is the bottleneck. The bottleneck here is, for example, 4, although you could actually just use, for example, a path with the bottleneck of 10. So this is the bottleneck, but again, in the previous example, we can see that if we go with the path that has the that has the largest bottleneck value, again in this algorithm it will actually prefer to go with this path and this path instead of actually choosing this path, because the bottleneck here is 1. And now the question is that how we can find the fattest path. It's just a simple modification over the digester algorithm to find the shortest path. You can also read this one in the textbook, the details of that, but it's a very good actually example to exercise. So the time complexity of finding the path is going to be the time complexity of the digester. So The rest of these slides are talking about another problem, a very interesting and related to the maximum flow problem. This problem is called the bipartite matching. So what is the problem? Let me actually just define it over some practical problem, for example. Assume that in a company, in a university, some advisor is supposed to help a student and help the companies to assign the students to some companies that they have applied for them to do the, for example, the co-op or internship. Just assume that every students have applied for a couple of different companies, and they have accepted by some of them, but each company just needs one student. Okay, and the advisor is trying to make sure that it actually assigns the maximum number of students to the companies. Okay, so how can we actually map this problem to a graph problem? You can actually just, here is an example that, for example, here is the name of the companies: Adobe, Apple, HP, IBM, Sun, Yahoo. And for each one, it actually here we have the name of the students who are interested, or they have applied and got the acceptance or whatever for each of the companies. Okay, so the best actually answer that make sure that maximum number of students will be hired is this assignment, that we assign Alice to Adobe, Bob to Yahoo, and so on. So that's going to actually be 6, the final answer. So if I wanted to actually map this problem to a graph problem, you can just assume that this is a bipartite graph. Remember, a bipartite graph was a graph that, an undirected bipartite graph here. A bipartite graph was a graph that we have two sets of, we can actually partition the nodes into two sets that there is no edge between the nodes which are in the same set. So here, these nodes is one set, and these nodes are one set. There is no edge between them, but there is edge between the nodes from one set to the other set. That's why we call it actually a bipartite graph. It's just like you can partition them into two disjoint sets. Partition the nodes. And so the bipartite matching problem over a bipartite graph is that you try to actually choose the maximum number of edges in this graph, so that every node will just actually have at most one edge. Okay, so you cannot, for example, choose this edge and this edge as well. So basically, it's just like every node will be matched with exactly one other node on the other set, at most, because some of them might not actually be matched. And the question is that we are looking for the maximum number of edges. We are looking for the maximum number of matches here. This is the bipartite matching problem. So how can we solve such a problem? I think this is very good that if you pause the video and think about the problem, and I'm going to actually just answer that what is a good algorithm and what is the relationship between this algorithm and the maximum flow problem. In fact, we can solve this problem using the maximum flow, the algorithm that we discussed for the maximum flow. And how we can actually solve that? The point is that I can simply added two nodes, a source node and a target node, and I can add some edges from the source to all of the nodes in one of the sets. It doesn't really matter that which set. So here, for example, I have added some edges from S to all of the nodes in this set. That's going to be actually the name of, for example, the name of the companies. And you add a node T, and you add an edge from all the nodes in the other set to the target. And you can actually just change the direction of all of these edges, and just make sure that you just actually make them one directed from the first set to the second set. And no, you can actually just see that if I assign the capacity of 1 to all of the edges that I have in this graph that I have created, the problem of finding the maximum matching in the original graph will be converted, will be actually reduced to the problem of finding the maximum flow over this graph if I apply the Ford-Falkerson algorithm here. And that's going to be very actually, in fact, fast, because I mean, it's not going to actually just get us stuck in any issue of the bottleneck or anything. But anyway, either use the Ford-Falkerson or Edmonds and COMP algorithm. You can simply solve this problem and find the the maximum matching in this bipartite matching problem. So this is going to finish the last lecture on network flow, and this is going to be covered in chapter 26 of the CLRS textbook.